up until now, all the algorithms that we've looked at, actually that's not true, all but the randomized algorithm that we've looked at, the randomized sorting and randomized selection, they had three properties. One is, well, they were deterministic. Actually, maybe this is more than three. They were always correct. Okay, so if it was an algorithm to, other than the randomized algorithm, even then that was just a matter of time. But if it was an algorithm to sort numbers, it was going to sort them correctly. If it was an algorithm to, what other algorithms did we do in this class? I'm blanking here. We must have done something besides sorting. String matching, finding all the patterns inside of a text. Okay, if that was the algorithm, if that was what that algorithm was for, it did it. Okay, it was always correct. And the third thing is that the worst case time is bounded from above by a polynomial function of the input size. Okay? So what kind of functions have we seen? What kind of upper bounds have we seen? We've seen order n. Okay, that was, for example, for pattern matching. We've seen order n squared. We must have seen order n squared. Who can think of an algorithm we saw in this class that has upper bound time order n squared? I think one of the dynamic programming algorithms we did must have been like that, right? Well, anyway. Or order n cubed. N cubed RNA folding was n cubed, right? Okay. So we've seen algorithms like that. We've also seen n log n. So all of these functions are nice polynomials of the input size. N is the input size in these problems, or at least it's the number of elements in the input. And polynomial because n is down here, but the exponent doesn't involve the variable, right? So these are all polynomial functions. So the worst case time for all of these algorithms is bounded by a polynomial function of the input size. That was a property of all the algorithms we've seen so far. Have we seen any algorithms that had a running time like 2 to the n? I don't recall that we have. I don't think we've done any algorithms that had that kind of time. Well, this is not a polynomial. This is exponential. Okay? The variable is in the exponent. That makes this an exponential function. Or n factorial is also an exponential, or some people think of it as super exponential, okay, because it's even bigger than 2 to the n. Okay, so certainly it's not polynomial. I mean, it's sort of an odd-looking function. But anyway, it's not bounded by any polynomial function. Its running time is not bounded in the big O sense by any polynomial function. So, all right. So hopefully everybody now knows what I mean when I say that the worst case time is bounded by a polynomial function. And generally in this world of algorithm design and algorithm analysis, we take the existence or non-existence of a polynomial time algorithm as sort of a rough dividing line between efficiency, an efficient solution and a non-efficient solution. Okay. Now that is rough, but when we get into NP completeness, you'll see more about why. Rough, you know. Who knows how to spell rough? I think I'm having one of those days. GH? Okay, yeah, thanks. I was never a good speller. Rough, actually, just a complete digression. Well, I was a TA, that's almost 40 years ago, for a class like this. I was in graduate school, and I was the TA and the instructor. It had an accident, and his writing arm was completely in a cast and bandaged. And so the way he wanted to do the lectures is he would do the lectures, and I would stand behind doing the board work. But my spelling was so terrible, he got really disgusted with it, and pushed me off to the side, and then anyway. I never could spell well. I can edit that out of the tape later. Okay, so a rough dividing line between efficiency and inefficiency, or efficient and efficient solution, and no efficient solutions, well, an inefficient solution is polynomial time. So if you have a polynomial time algorithm that solves your problem, that's considered roughly efficient. If it's exponential time, that's considered roughly inefficient. But if you look more closely, of course, there are distinctions. I mean, you may have an algorithm that runs in n to the 6,000. That's polynomial, but that's growing very, very rapidly as a function of n, as compared to, maybe 2 to the n over 6,000. Okay, that's exponential, but you can push n pretty high before you start running into horrible trouble. Still, this is a rough dividing line, and usually we don't see functions like that anyway, polynomial functions. Okay, this is all by way of saying that the algorithms we've seen, except for the randomized algorithm that we looked at, all have these three properties. But the truth is that for most problems of interest, we don't have an algorithm that has these three properties. So you can consider this as sort of the gold standard of what we want. Always correct, worst case running time, deterministic. Deterministic really means that we get worst case results rather than results in expectation, or either expectation of the running time or in terms of how often they're correct. So this is the gold standard. Okay, but we don't always have algorithms. In fact, we actually rarely have algorithms that satisfy all these properties. I mean, there are enough of these that we can make textbooks out of them and teach whole courses about them and so on. They're not that rare, but if you just take a general, typical problem out of the air, it often lacks a solution that satisfies those three properties. So what to do? So there are several approaches to that. What to do when no gold standard solution exists? Okay. Well, one thing is you can just give up. And actually, that's common. But if you don't want to do that, then you want to relax one of these three properties that you insist on to be a gold standard solution. Well, varying determinism, I was about to say that generally doesn't help, and I'd probably stick with that. But mostly we vary these two. Okay, you invent algorithms that are often correct, mostly correct in ways that you can quantify and you can prove things about, but they're not always correct. So algorithms that are fast in worst case but aren't always correct. Or you vary this, algorithms that are always correct but aren't always fast in worst case, aren't always polynomial time in worst case. So today we're going to talk about algorithms where we vary this, or where we relax this. Algorithms which are not always correct, but we can say something about how incorrect they are. And that's what leads us to approximation algorithms. Okay, and usually, well, all the approximation algorithms that I know of are about optimizing some value of some function. So these are not questions that does something exist or not exist. These are problems where we're trying to minimize something or maximize something. We've seen many problems of that sort. And what we're trying to do with an approximation algorithm is get close to the optimal solution. If it's a minimization problem, we want a fast algorithm, a polynomial time algorithm, that is not always guaranteed to get the optimal, to get the minimum, but when it doesn't get the minimum, it doesn't get a solution that's too far from the minimum. So we're able to prove that its deviation from the actual minimum isn't too great. And if it's a maximization problem, then we'd want to prove that our deviation wasn't that great either, but it would be on the other side. So let's say for a minimization problem, okay, so we're trying to minimize some quantity in some problem setting. I haven't given you any specific problems yet, but you know what a minimization is for various problems. So for a minimization problem, let's let just C star represent, okay, C star of I represent the minimum value when the input is I. Okay, so just notation. We have some problem, I haven't told you what it is, but we're trying to minimize something with respect to that problem. If we give the problem, if the problem instance is represented by I, C star I is the minimum value, the value of the minimum value of the optimal solution when the input is I. Okay, so then we want an algorithm whose running time is bounded by a polynomial. Polynomial function of the input size, okay, where C of I is the value of the solution given by the algorithm. And C of I over C star of I is less than or equal to some constant value. Okay. So integer. And let's just say, well, a constant value. And this is for any I, or for all I. Okay, this is a lot of words. And I haven't even shown you a single problem yet, but this is what we want. We want an algorithm whose running time is polynomial, so it's a fast algorithm. It's deterministic, polynomial time. And it puts out a solution whose value is C of I. It's just denoted C of I. And then we're interested in the ratio. Well, how close is C of I to C star of I? Okay? What's the best you could hope for? What would you want K to be here? 1, right. In fact, if this was 1, you couldn't ever be less than 1, right? Because this already this represents the best that's possible, the smallest that's possible. So it couldn't be less than or equal to 1. So you would, of course, you would like to have an algorithm which is equal to 1, which just means there's a polynomial time algorithm who always puts out a value, a solution that's optimal. Okay? But we're in this context where we don't think that's possible. So less than or equal to k, what do you want for k? Well, as small as possible, larger than 1. Okay? So maybe, 1.16. The ratio of the what the algorithm puts out to what the optimal is less than or equal to 1.16, etc. There aren't very many of those. There are some around there. It's not, though, that's not uncommon to get something like 2. Algorithms where the ratio of what the algorithm puts out, the fast algorithm puts out, to what's the actual best is bounded by 2. And there are algorithms where it's 3. There are algorithms that go up to 5, 6, 7 that people have found interesting. There are a couple that I know of that are like 1.5, 1.3, and so on. But 2 is a very common ratio. Okay. The only thing that would be better than this kind of result is if you could have a result that says Ci is less than or equal to C star I plus some constant. Okay? That would be a stronger result than this kind of ratio. This says you're never more than the optimal plus a constant, which actually means that in ratio, if you get to bigger and bigger optimal values, your ratio of what the algorithm produces to the optimal gets smaller and smaller. But and there are results like that. In fact, there are even results like this, where the values of the solutions are integral, and we have a fast algorithm where its deviation from the optimal is never more than 1. Okay, so that's pretty amazing, pretty good, and yet we don't have an algorithm, a fast algorithm that actually is guaranteed to produce the optimal. Okay, so I've told you what we're going to do. The kind of result we're going to get is where this ratio is bounded by a constant, and 2 is a common one. So let me look at a particular algorithm, and then next time you'll see another one. So this is the center selection algorithm. And this is on page 606 of the book. So it's section 11.6. No, 11.2, sorry. 11.2 in the book. And so in this problem, we have n sites. You can think of these as cities. And we're going to pick k. K is not related to that k, but it's used in this problem. We'll pick k centers. And what's a center? So actually, and a center could be any point. It doesn't have to be among the sites. It could be any point on the plane. And so if you want to think of this in some kind of concrete terms, these are houses, and then we have a problem of picking places to put cell phone towers. Okay, and the cell phone towers can be anywhere. They don't have to be right where a house is. Okay, so this is kind of reminiscent of one of the homework problems we had where the houses were on a straight line, although initially it was ambiguous to whether that was, you wanted to have the houses on a straight line or not. And so here we have n sites, and we're going to pick k centers. And we want to minimize R to guarantee that no site is, now I'll put it the other way around, every site is within distance R to some center. So we've already fixed how many centers we're going to pick, K. That's part of the problem input. But you still have to figure out where you want to place them in here so that you minimize R, which is called the radius, anyway, that guarantees that every site is within distance R to some center. So if I use these x's as centers here, then we would look for the closest. For every site, we would look at what's the center that's closest to it. Some of these we can eyeball. This one, maybe less clear, and so on. And maybe that way. Okay, so every site now has a closest center. And in terms of this picture, what R is the greatest distance. It's the maximum distance of any one of the sites to its corresponding center. So everybody understand what I did here? I just put down some centers marked by X's, and then for every one of the original sites, of course, now I've kind of lost what a site is. So here was a site. For every one of the original sites, I'm showing you which center is it closest to, and then the longest distance between a site and its corresponding center is equal to R. That just eyeballing this, that looks like the longest one. Okay? And what we want to do is we want to minimize what that radius is. We want to minimize R to guarantee that every site is within distance R to some. Now you can imagine this problem in somewhat reverse. You might be given R, and then you'd want to minimize K. Right? That's the version we saw in the homework. We had sites, which were the houses, and then R was what in that? Anybody remember what R was in that problem? It was 4 miles. Yeah. So every house had to be within 4 miles of some tower, cell phone tower, and then we wanted to minimize how many there were. So different variants of the same sort of problem. Now the houses or the sites are not on a straight line. So in fact, this is kind of like what we might have thought initially was the homework problem, but I think it was clear by context that they wanted those on a line. Okay, well, in fact, okay, so we have a problem. This is the problem. We have something we're trying to minimize. We're trying to minimize the quantity R. All right? So this fits within the context of a minimization problem. And you can think of algorithms that would pick K sites. It's not even clear how you'd pick to think of an algorithm that's guaranteed to minimize. I mean, a finite time algorithm. Because there's certainly an infinite number of places you can put down these X's. We haven't quantized this at all. So there's an infinite number of ways that you can place down X here. And so it's not even clear that you could think of an algorithm that runs in finite time that's guaranteed to give you the minimum R, let alone trying to get an algorithm whose time is bounded by a polynomial in N, and let's say we'll throw in K as well. So a polynomial function of N and K, essentially the input size. And in fact, we don't know one. We do not know a deterministic, always correct, in this case meaning it'll get you the minimum R, algorithm that solves this whose worst case running time is bounded by a polynomial function of the input size. That's the state of the world. And if anybody thinks of one, let me know. You'll see after we talk about NP completeness that would have a huge consequence, and as a minimum, I think there's $1 million prize for anybody who can find a polynomial time algorithm for this problem or many others, any of many others. But you'll understand that later. But right now, just take it as a fact that we don't know any algorithm for that problem that has these nice properties. But we do know approximation algorithms. We know an algorithm whose running time is bounded by a polynomial, and it picks k sites, and it's guaranteed that the distance of every site to some one of the centers that it picks is less than or equal to 2r. If r is the absolute minimum, but we don't know what r is, then the algorithm will produce a solution where we can prove that the distance of any one of the sites to a center is less than or equal to 2r. Okay? So I want to really finish this in one lecture, so let me just show you what the algorithm is. Okay, actually, in the developing of this algorithm, to develop the algorithm, we're going to suppose we know R. Okay, so initially in this algorithm, we're going to use R to pick out a set of centers where we can then prove that the distance of any site to one of the picked centers is at most 2r. But R is going to be part of the algorithm. So we're really cheating, right? If we knew R, well, not absolutely sure, not actually obvious if you knew R. No, it's not true that if you knew R, you could easily find what the centers are. But certainly, in this problem, you're not supposed to know R. But as a thought experiment, as developing an algorithm, we can pretend for a while that we know R, and then later see how to get rid of that assumption. So this is just an expositional matter. Okay, so here's the algorithm. We start out with, the set of the input sites are in set S. Okay? So the algorithm begins by setting S prime equal to S. Okay? And C equal empty. So C is going to be the points that we're going to use for centers, and S are the sites that we have to cover. We have to have the centers have got to be within a certain distance. Well, yeah, we're going to pick, K, we're going to pick K centers. All right. Then, while S prime is not empty, okay, pick any site that's still in S. S prime, sorry. And add little s to C. Okay? Well, that seems kind of indiscriminating. I mean, it doesn't seem like it's a terribly smart algorithm. All it's saying is just pick a point. Pick one of the sites and make that a center. All right? So the next step is the important one. Then we're going to delete all sites in S prime that are within distance 2r from this S we just picked. Okay? So and this is the end of the while. Okay, so just in a little cartoon, here are the sites, and let's say R, we know R, that's too big, that's R. Okay, so what the algorithm says is just pick a site randomly, arbitrarily, whatever, doesn't matter. And then any other site that's within 2R, so this is R, this is 2R, any other site that's within 2R, remove it. Okay? So, I don't know, if this is the center of that circle, 2R is, I don't know, like that. Okay? Not a very good circle, but you see the point. So these guys go away, because you're going to delete all those sites from S prime that are within 2R from S, from little s. Now this is little s. And so these guys go away. All right? And so they are all those sites are within 2R to this center that you just picked, right? Okay? And then, well, S prime is still not empty. So we're just going to pick any other site, maybe this one, okay, and delete anything that's within 2R of it. And we still have something left, so maybe we pick this site, and 2R, oh, that doesn't get anybody, right? And we still have somebody left. We pick this one, and within 2R of that, we get that one, and now we're done. So in this little cartoon, we picked 4 sites, okay? And where is K in this algorithm? Oh, yeah, okay. It's on the other side of the sheet. Okay. So you do that, okay? And then, as part of the algorithm, if what you did is less than or equal to, if the number you picked was less than or equal to K, okay, that's the number of centers you're allowed to pick, okay, then output that guy. And if C is greater than K, then claim no set. There is no set of K sites such that all K centers, such that all sites are within distance R to some center. Okay, this is the way the book does it, and it's really messed up. Just a side comment. Because the book starts off by saying, we actually know R. Okay, so we're given the input R S, and then, of course, what the target K is. Okay? And by the definition of the problem, R is a radius, is a distance that should work. Okay? The problem is given a set of sites and given a k, which is the number of centers you can pick. R is that smallest distance such that you can pick k centers so that everybody's within radius R. And then they give an algorithm which has within it the possibility of failing. Okay, so they did this sleight of hand where they said you're solving this one problem where when you know R, there's definitely a solution, and then you give an algorithm that includes the possibility that there is no solution. Okay, so let me just alert you to that they did that this kind of sloppy thing. Okay. So I want to kind of deviate from what the book does and go back to the assumption that given S and given K, R really is the minimum distance, so this can't fail. This algorithm is going to succeed. All right. So this part, it's okay to have it in the algorithm. It's just this is always going to happen. Okay. This is always going to happen, right? It's never going to fail. So they want to put in this extra code in their program, fine, but we don't need it because R really does this. So I want to prove the following, which deviates a little bit from the way they do it in the book. Yeah, okay. Claim the algorithm ends with C less than or equal to K. Okay? That is, we're going to pick, at most case, centers, and of course, everybody is within a distance 2R from one of those centers because the algorithm got rid of all the sites. Okay. So here's the idea. In the optimal, suppose we actually know the optimal solution. And I'll call it C star. So here are the sites, and then we have the places where we're putting the centers. And everybody is within distance R to one of the centers, but I'm only going to look at one center at the moment. Okay? So everybody is within a distance R to some center. So let's say here. That's within distance R. And so these are the guys who are within distance R of this center that's picked in the optimal solution. Okay? So there's a set of centers that are within distance R of, sorry, a set of sites that are within distance R of that center. Okay. Now suppose that the algorithm picks one of these sites to be one of the centers. So the algorithm is picking sites to actually be centers. So the algorithm is going to pick a site, and that site is within distance R of some center, right? Of some center in the optimal. So this is a site that the algorithm picks. The algorithm picks. This is the center in the optimal solution such that this is within distance R of that. Now look at all the other guys that are within distance r of this center. They're within distance 2r of this site. Okay? So all the sites within distance r to center, I'll give this center a name, C star, center C star in the optimal, and this one was little s, are within 2r distance to little s, right? Why within 2r? Well, I mean, if you can go within r to here and within r there, that's, if you went straight, it's even less than that. So everybody that this center covers, all the sites that this center covers, are within distance 2r of this site that's chosen as a center. Okay? So, all right, that's one fact. And then, in the algorithm, you pick this as a center and you get rid of all of these, sites because they're within distance 2r. All right? And then you pick another guy, and he's within r to some site. Now, this next one that you picked is within distance r to some other center. Is that within distance r of the center associated with the first site you picked? Can't be within distance r, because if it was within distance r to this one, it'd be within distance 2r to that one, and it would have gotten deleted. So as the algorithm proceeds, each site that you pick as a center is within distance r to a different center in the optimal. Okay? So that is a crucial thing. I'm running out of time. As the algorithm proceeds, each site put in S prime is within distance r to a different center in the optimal. Okay? So we're mapping. This says we're mapping every site that's selected by the algorithm. Every site that's selected to be a center by the algorithm is mapped to one of the centers in the optimal solution. And they're each mapped to different centers. Okay? That being true, how many centers does the algorithm select? The optimal, remember, has k centers. Now we're mapping every center picked by the algorithm to a different center. So how many centers does the algorithm select? K, or even less possibly, at most K. And everybody, all the sites are within 2K of one of the centers selected by the algorithm. We already argued that. So this algorithm picks at most K centers, and it has the property that every other site is within distance at most 2K from one of the centers that's picked. So we've achieved what we wanted, which was a polynomial time algorithm. Well, you can argue, you can convince yourself this is polynomial time. It's a fast algorithm, such that it picks at most K centers, and the distance of any point, any site, is at most 2K. That distance is less than or equal to 2R, I'm rushing, 2R of one of the chosen sites. Now, there's only one thing wrong with this algorithm in terms of the result we wanted, which is, yeah, we're assuming we know R. Okay? And we use it in this algorithm to delete all sites that are within 2R of the point we picked. Okay? All right, how are we going to get around that? Well, if you think about the proof that I just rushed through, the key thing in that proof is that when you pick a site by the algorithm and delete some sites around it, the next site you pick is at least 2R away from it. You're killing off everything that's within 2R, and so the next site you pick has got to be outside of the circle of 2R. Okay? And if you can just guarantee that property, then that's enough to make sure that the result you get is within 2R. The result is the same as what we want. So how do we achieve that when we don't know R is the following. We start out arbitrarily picking a site, okay, and then the next site we pick is going to be the farthest from it, the farthest away from the site we've picked. Because that site, if any, suppose we did know R, and we kill off the ones that are within 2R, if there's anybody left, then the farthest one from the one we just picked will certainly be left. Okay? So you pick one, and then the next one you pick is going to be the farthest away from it, and the next one you pick is the farthest away from it, and so on. And when do you stop? Well, you stop when you picked K of these sites. Okay? So you pick K of the sites, and you're effectively doing what this would have done. It knew R, but you don't need to know R because you're just always picking the farthest. You pick K of them, and then you can figure out what the radius of that solution is, and you know you're within distance 2R, a factor of 2 of what the actual minimum radius is. Okay, this went fast and somewhat different than the way it's done in the book. Read that section in the book. But don't be confused by the fact that it says this will work and then, oh, but maybe it won't work. And that kind of sleight of hand that they did.